name's Tamsin and welcome to the session on photons and electrons. I'm excited to be working with you today and let's jump right in. So light has a wave-particle duality, and this means that light has the properties of a wave, and so it undergoes reflection, refraction, diffraction and interference. It has wavelengths, frequency and wave speed, which we know c is equals to 3 times 8 meters per 3 times 10 to the power of 8 meters per second to the negative 1 in a vacuum. However, light also has the properties of a particle, and a particle of light is called a photon. We use this equation E is equals to hf, where E is equals to the energy of the photon. H is Planck's constant, which you can find on your data sheet, and F is the frequency of the light. Visible light is just a part of the electromagnetic spectrum, and when we talk about light in this section, we mean all electromagnetic radiation. So you can see here there's visible light and where it falls on the electromagnetic spectrum. On the left-hand side, we have high frequencies and light with short wavelengths, which then have high energy. This includes waves like gamma rays, X-rays, UV. And on the right-hand side, you can see that we have a low frequency with a long wavelength, which means lower energy. And this is things like microwaves, radar, and radio. So the photoelectric effect. When light of sufficient frequency shines on a metal surface, electrons are going to be ejected. So you can see in this diagram, we have a photon and it's hitting a metal surface, and electrons are going to be ejected. What's really important to remember is that one photon can only eject one electron. So when we talk about sufficient energy, we're talking about how electrons are held to the surface of the metal through the forces of attraction between the electrons and the metal cations. So in order to eject an electron, we need to give it enough energy to overcome this force of attraction. The energy of the photon gets transferred to the electron, and therefore sufficient refers to the photon needing to have more energy than what the electron needs to be ejected. So the work function is the minimum amount of energy the electron needs in order to be ejected from the surface of the metal. We also talk about threshold frequency, which is the minimum frequency of light needed to eject an electron from the surface of a certain material. So in order to have sufficient energy, our energy needs to be greater than our work function, or our frequency needs to be greater than our threshold frequency, or our wavelength needs to be smaller than our threshold wavelength, because remember, the smaller the wavelength, the greater the energy. So all of those properties on the left in orange are then the properties of the incident light, whereas the ones in blue are the property of the specific metal. So now let's take a look at an example. So it says the work function of a particular metal is 2.9 times 10 to the negative 16 joules. Question A asked us, what is the threshold frequency of the metal? Well, we can use the equation W0, or work function, is equals to Planck's constant times by the threshold frequency. We then have been given the work function, and we know that that is 2.9 times 10 to the negative 16 joules. Our Planck's constant you can find on your data sheet, and that is equals to 6.63 times by 10 to the negative 34. And then our threshold frequency is what we're trying to work out. So if we do a little bit of rearranging, you should get that the threshold frequency is equals to 4.37 times by 10 to the 17 hertz. Remember that frequency is always measured in hertz. Right, let's move on to B. So B asked, what is the maximum wavelength of light that can eject a photon from the metal surface? Well, we can use our equation C is equals to F naught times by our threshold wavelength. And what we're going to be looking for is our threshold wavelength here. So on your data sheet, you can find C, which is equals to 3 times 10 to the 8. That's a 10. And it's equals to our threshold frequency, which we've just worked out. And that is 4,37 times 10 to the power of 17 times by our wavelength. If you do a little bit of rearranging, you should get that your wavelength is equals to 6,86 times by 10 to the negative 10 meters. If you convert that to nanometers, it would be 68,6 nanometers. And that is our wavelength. So if we take a look at question C, it's asking, will light with a frequency of 8 times 10 to the 14 hertz eject electrons from the surface of the metal? Well, in order to answer this, we have to look at our frequency and our threshold frequency. So our frequency should be greater than our threshold frequency if we want to observe the photoelectric effect. So our frequency, so I've mixed these around. This should be the other way around. Let's erase this quickly. Okay. So we need our threshold frequency to be bigger. So our frequency was 8 times 10 to the 14, and our threshold frequency was 4,37 times by 10 to the 17, what we just worked out over here. So from this you can see that our threshold frequency is greater, and so we will observe the photoelectric effect and electrons will be ejected. So what is the significance of the photoelectric effect? Well, this establishes the particle nature of light, because in the beginning we said that it has a dual nature. It also establishes the quantum theory. So from our picture here that we showed earlier, we now get a new equation, which says E is equals to the work function plus the kinetic energy. So you can see E here relating to the photon, the work function, and the kinetic energy. So another way that we can rewrite this equation is HF as our energy is equals to Planck's constant times by frequency. We also know that our work function is equals to Planck's constant times by our threshold frequency. And you know that EK is equals to a half mv squared. Another way we can write this equation is using our wave formula. Right, so let's look at another example. It says the threshold frequency of a particular metal is 3 times 10 to the 14 hertz. Light with a wavelength of 4 times 10 to the negative 8 meters is incident on the surface of the metal. So now question A asks us, will electrons be ejected from the surface of the metal? Again, for A, we can use our equation. C is equals to the frequency times the wavelength, because we know what C is. C is just 3 times 10 to the power of 8. Our frequency is what we're looking for, and they've given us our wavelength, which is 4 times 10 to the negative 8 meters. Always use your wavelength in meters. So then if we calculate our frequency, we will get 7,5 times 10 to the 15, and remember frequency is always measured in hertz. So now we look, is our frequency greater than our threshold frequency? If so, then we will observe the photoelectric effect and electrons will be emitted. So, is it greater? Yes, it is. So we will observe the photoelectric effect. Question B now asks us, if so, what is the maximum kinetic energy with which the electrons will be ejected? Well, we're going to have to use that equation that we just learned about on the previous slides, which is E is equals to the work function plus the kinetic energy. So we know that E is equals to hf. The work function is equals to the Planck's constant times by the threshold frequency plus kinetic energy. So let's start filling in these values. Planck's constant is 6.63 times 10 to the negative 34. Our frequency is 7.5 times 10 to the 15, and that's this frequency that we worked out in A. Again, Planck's constant is 6.63 times 10 to the negative 34. Our threshold frequency is 3 times 10 to the power of 14. And then we plus kinetic energy. So now with a bit of rearranging and calculator work, we can work out our kinetic energy, which then comes to 4,78 times by 10 to the negative 18, and this is measured in joules. If we take a look at this graph of kinetic energy versus frequency, we can see how we can arrange the equations in order to get the standard straight line equation, which we're used to, which is y is equals to mx plus c. So here's our equation in the form that we are used to seeing. And if we do a little bit of rearranging, we can put the kinetic energy on the left-hand side, and then we'll take this over to the other side so that our work function becomes negative. And if we relate this to the equation of a straight line graph, y is equals to mx plus c, you can see how our kinetic energy is on our y-axis. So that relates to our y variable. We can see that frequency over here is on our x-axis. So frequency relates to our x value. This means that h is our gradient, which is really important to note. So our gradient is equals to Planck's constant. And plus c relates to our work function, which is now negative. If you had to extend this axis, you'd see that it would cut it somewhere around here, which would then be our work function.